This is Keith Wiggins. I'm with PAG Waste Management. We're talking about principles of gasification, chapter 4 this time, with the Handbook of Biomass Downdraft Gasifier Engine Systems. Let's get started. Chapter 4, Principles of Gasification, Introduction. Gasifiers are relatively simple devices. The mechanics of their operation, such as feeding and gas cleanup, also are simple. The successful operation of gasifiers, however, is not so simple. No neat rules exist because the thermodynamics of gasifier operations are not well understood. Yet, non-trivial thermodynamic principles dictate the temperature, air supply, and other operating variables of the reactors that we build. It is a tribute to the persistence of experimentalists that so much progress has been made in the face of so little understanding. Nevertheless, it's been the experience in related fields such as oil, gas, and coal combustion that once the mechanism at work are understood, the engineer is able to develop cleaner, more efficient processes. Fortunately, most of the knowledge acquired in these fields can be applied to enhance our understanding of gasification processes. In this chapter, we present a summary of the underlying processes that occur during biomass gasification. We will attempt to keep the explanation simple because each fundamental process is basically simple. Chapter 5 gives a more extensive description of the operation of specific gasifiers, and details are available from the literature from those interested in a more thorough explanation. So they have some references for you. Biomass thermal conversion process. Thermal conversion process for biomass involves some or all of the following processes. First, pyrolysis. Biomass plus heat is equal to charcoal, oil, and gas. Gasification, biomass plus limited oxygen is equal to a fuel gas. And combustion, biomass plus, I always get this word wrong, stoichiometric oxygen is result in hot combustion products. Thermal processes typically have a high throughput and can, in principle, operate on any biomass form. Biological processes only operate on some of the components of biomass, usually the cellulose. Cellulose is a linear polymer of anhydroglucose units. Hemicellulose is a mixture of polymers of 5 and 6 carbon anhydrous sugars. And lignin is an irregular polymer of phenylpropane units. In biomass, these three polymers form an interpenetrating system or block copolymer or block copolymer that varies in composition across the cell wall. Nevertheless, in large samples, there is relatively constant atomic ratio of CH1.4 and O.6. The ratios will vary slightly with species. Coal is typically about CH.9, O.1, but varies more widely in composition. The relationship between solid, liquid, and gaseous fuels is easily seen in a figure down below, where the relative atomic concentrations of carbon, hydrogen, and oxygen are plotted for a variety of fuels. Here it is seen that the solid fuels, biomass, coal, and charcoal, lie in the lower left segment of the diagram. We'll see that in a second. Liquid and gaseous hydrocarbon fuels lie in the upper left section. Carbon dioxide and H2 and hydrogen are joined by the bisector of the triangle, and the combustion products of fuels, CO2 and H2O, lie on a vertical line on the right. I'll explain it a little bit more when we get there. Thermal conversion processes for biomass are indicated by the arrows. Here it is seen that the conversion process moves the chemical composition of biomass to liquid or solid fuel regions, either by biological or thermal means. In some cases, such as oxygen-air gasification, the processes are spontaneous. In other cases, such as steam gasification, considerable energy must be expended to cause the change. For biomass pyrolysis, pyrolysis is the breaking down or lysis of material by heat, pyro. It is the first step in the combustion or gasification of biomass. When biomass is heated in the absence of air to about 350 degrees centigrade, pyrolysis, it forms charcoal, chemical symbol C, gases, carbon monoxide, carbon dioxide, H2 or hydrogen, H2O, and CH4, and tar vapors with an approximate atomic makeup of CH1.2 and O.5. The tar vapors are the gases at the temperature of pyrolysis. The tar vapors are gases at the temperature of pyrolysis, but condense to form a smoke composed of fine tar droplets as they cool. All the processes involved in pyrolysis, gasification, and combustion can be seen in the flaming match down below in figure 4.2. The flame provides heat for pyrolysis, and the resulting gases and vapors burn in the luminous flame in a process called flaming combustion. After the flame passes a given point, the char may or may not continue to burn. Some matches are chemically treated to prevent the charcoal from smoldering. When the match is extinguished, the remaining wood continues to undergo residual pyrolysis, generating a visual smoke compared to the condensed tar droplets. So let's go to figure 4.1, and I'll try and give it a good explanation. So the phase diagram shows the relative proportions of carbon, hydrogen, and oxygen in solid, liquid, and gaseous fuels, chemical changes during the biomass conversion process. Part A of the diagram, right here, is the phase diagram showing the relative proportions of carbon, hydrogen, and oxygen in solid, liquid, and gaseous fuels. The diagram shows that solid fuels, represented by biomass and coal, have a high proportion of carbon and low proportion of hydrogen. Liquid fuels, represented by the liquid fuels, have a lower proportion of carbon than solid fuels and a higher proportion of hydrogen. Gaseous fuels, represented by the gaseous fuels, have the lowest proportion of carbon and the highest proportion of hydrogen. Part B of the diagram shows the chemical changes that occur during biomass conversion processes. The diagram shows that biomass, cellulose, and lignin can be converted to gaseous fuels, carbon monoxide, H2, and HCH4, through a series of gasification processes. The gasification processes include pyrolysis, letter P. The process involves heating biomass in the absence of oxygen. It produces char, liquid fuels, and gaseous fuels. Steam process, S. This process involves heating biomass with steam. It produces hydrogen and carbon monoxide. Oxygen process, O. This process involves heating biomass with oxygen. It produces CO2 and heat. The diagram also shows that the proportions of the products can be varied depending on the gasification process used. For example, the pyrolysis process produces more char and liquid fuels than the steam or oxygen process. Here are some additional details from the caption of the diagram. So CE refers to cellulose, L refers to lignin, and B refers to biomass. And so if we move on to the next item, the burning match here, the image is related to pyrolysis, gasification, and combustion. It depicts these processes occurring in a flaming match. Pyrolysis is the first stage pictured at around 400 degrees centigrade. Here, the wood undergoes thermal decomposition in the absence of oxygen. The process breaks down the long chain molecules in the wood into smaller molecules, including water vapor, oil vapors, and gases. Combustion occurs between 600 and 1500 degrees. In this phase, the oil vapors released during pyrolysis crack into hydrocarbons and tar. Additionally, the gases released during pyrolysis combust. This is the burning part of the flame you see. As the temperature rises, the tar and soot also combust, releasing more heat. Gasification isn't exactly labeled in this diagram, but it can be considered to be happening alongside combustion from 600 degrees upwards. During gasification, the biomass, or wood in this case, is heated in a controlled environment with limited oxygen. This produces a combustible gas mixture, which can be used as a fuel. In the context of the match, some of the gases produced during pyrolysis and the later stages of burning would contribute to this gasification process. So we continue with pyrolysis. A more quantitative picture of pyrolysis is obtained through the thermogravimetric analysis, TGA. In this technique, a small piece of biomass is suspended on a balanced pan in a furnace, and the temperature is increased with time at a known rate. An example of the residual weight change experienced by a small sample of flax sheaves heated at a rate of 40 degrees centigrade per minute is shown in figure 4.3. One sees that moisture is released first at about 100 degrees centigrade, followed by the volatile materials at 250 degrees, 450 degrees centigrade. These temperatures are important in understanding pyrolysis, gasification, and combustion. According to the figure, a fraction of char and ash remain in the end. If air is allowed to enter the system after pyrolysis, the carbon or char will burn, leaving the ash as the final product. Each form of biomass produces slightly different quantities of char, volatile material, and ash. Knowledge of these quantities, as well as the temperature dependencies of the reaction and associated weight losses, are useful in determining gasifier operation and design. The results shown in Figure 4.3 are qualitatively similar to those obtained in approximate analysis of most biomass, but are not identical because heating rates are higher and samples are smaller in TGA. The curve in Figure 4.3 represents pure pyrolysis in an inert gas such as nitrogen or argon. If pyrolysis occurs in air, the curve drops more steeply within the region from 250 degrees to 400 degrees centigrade. Because the char and the products are oxidized also as the char burns, it eventually reaches the ash line between 400 degrees and 500 degrees centigrade. Figure 4.3, more than 80% of the total dry mass of the sample is volatilized below 500 degrees centigrade, leaving an additional 10 to 20% of the original mass of carbon for conversion to gas. It is now recognized that the volatile matter is composed of monomers, such as well as other fragments of cellulose, hemicellulose, and lignin polymers that make up biomass. It is even also recognized that up to 65% of the biomass dry weight can be converted in this water-soluble wood oil, which potentially may form the basis of a new process for wood liquefaction. Unfortunately, these oils are corrosive and highly oxygenated, so that further processing will be required to make high-grade liquefied fuel or liquid fuel. However, they have been burned successfully in industrial boilers and turbines with minor modifications required for the burner. So in this image, this TGA analysis, it's the methods used to measure a weight of a sample as it's heated in a controlled atmosphere. In this case, the atmosphere is absent of air. The x-axis of the graph shows the temperature, and the y-axis shows the percent of the initial weight remaining. The accompanying text describes the different stages of weight loss observed. And with the sample at 40 degrees centigrade and the recorder speed of 4 centimeters per minute, the curve shows 3 distinct stages of weight loss. Moisture loss up to 200 degrees centigrade, the initial weight of evaporation of moisture in the sample, around 4% of the weight is lost in this stage. Volatilization, the light organics, 200 to 400 degrees centigrade. In this stage, the hemicellulose and cellulose in the flax chips decompose and are driven off as gases. This accounts for a further 75% weight loss. Degradation of lignin occurs between 400 and 600 degrees. Lignin is more resistant to thermal decomposition than hemicellulose and cellulose, so it decomposes at a higher temperature range. This stage accounts for an additional 18% weight loss. All right, so we are going to pick it up at 4.2.3, combustion of biomass, next time. Thank you so much for listening, and I'll talk to you later.